let's look at a scenario wherein the charge is released at an angle. So we have to understand that charge, when it's released parallel to our magnetic field, nothing happens to that, while perpendicular, when it's released perpendicular, it will go in circular motion. Now it's a combination of both, right? So when I tell release at an angle, say this is a magnetic field, this is a charge at this point. So it's moving in this way, or it started entering in this way. It entered this way. The question is, what happens to this now? To understand that, I already have pre-drawn a diagram. Here we have the velocity component. This can be resolved to parallel and perpendicular to your magnetic field. Now, we know that parallel component will not get affected by magnetic field. So this will just make it move up, while this will make it move in circular path. Why? This is perpendicular component to B. So basically, if I use my right hand rule now, palm rule, so the magnetic field is up, my vector component is to the right. So this will be facing in our direction, right, guys? So because of that, this will go in this way. Let me do this. So it will basically go this way, is it not? But it has to go up also. So what will happen? So basically, it will go this way. Does it make sense? It's going up as well, it's going circular. If I watch it from the top, so you can clearly see that it will be looking at, we are looking at a circular path. If I watch it from the side, not looking at side is our point of view is side. Instead of looking at it going circular and all of that, if I just take a line, it will look like as if it's going slowly up. The displacement, upward displacement, is also seen. So both of them are acting. So this is what we are trying to see. We are trying to see what is this circular path's radius and what is the time period for complete revolution and what is the distance between this circle and the bottom circle. Basically, how do you do that? Take one point, the same point at the bottom. What is the distance between them? That's what we are trying to look at. Okay, so any helical structure, we have this two distance. We can take it between any 2 points, to be honest, even this two distance. So this is known as pitch. We'll define the term pitch. So this is not for exam. Not for exam. You can't keep doing this for exam. This is only for understanding. Okay, so basically it goes something like this. So you guys can write it in your books, but not for your exam. Right? Now let's come to the actual thing. So what we're looking at is we're trying to find the radius of this circular path, time period, time for one this revolution, rotation, going in circular path, that is, and pitch. So revolution, rotation. Anyways, that you guys can see. Let's figure out this. How? Let's take a charge of Q. Let's have a magnetic field whose strength is B. Let the initial velocity be B. Not B, sorry, V. And the angle be theta. The magnetic field that the charge will encounter is given by Q, a cross product between V and B. Right? That's very clear. Now, when it comes to the vector component, we can resolve it. So we can resolve it parallel to the magnetic field line. And then, sorry, this is parallel and that's perpendicular. So the perpendicular component will be VE. So the angle over here is, oh sorry, I have to draw it actually. So the diagram looks like this, guys. I need to give you guys a diagram first. Same thing, just that in exam, this is how we'll draw it. There's some slowdown. Okay, so let that be our magnetic field line direction. And that is not what I wanted actually. I wanted it to be at an angle, theta. Okay, measured this way. Now we are resolving this into two components, right? This will be your perpendicular component, this will be your parallel component. So your perpendicular component is related how? Is related with the help of sine, right? That would be opposite, yes, sine of theta. And parallel component is V cos of theta. Agree? Parallel is cos, correct. See the diagram, simple trigonometry. So we know for a fact that the motion in a magnetic field, the magnetic field only affects the perpendicular component. So only this component of the velocity causing circular motion. The parallel component remains unaffected and causing the particle to move in helical path. So this is how you have to present your answer. Now the centripetal force. Who will give us the centripetal force? It's given by, I have written over here, centripetal force is given by your magnetic field, right? So that's the cause basically. Of course, even the charge itself. So we have the force, centripetal force given by mv square by r, right? That's the formula. So on substituting, Fp and V, this in this case perpendicular. So what do we end up with? We know this is QVP sine theta, and this is MV sine theta the whole square divided by R. So a bit of simplification, and R will be equal to MV square sine square theta, or let me do it in the next step. Aram se QVP sine theta is equal to, so V and V square, this and this, and so we have R, therefore R is equal to MV sine theta component divided by QP. Agree guys? Have a look. Don't worry, there is a usage for this. We're not just blindly doing it. That's your expression for radius. Now, time period. What will be the time period? So time period, we can figure it out with the help of time period is equal to the distance by your velocity. So distance for this is, we have taken it as r, right? Yeah, 2 pi r divided by velocity is v, which component? Sine theta component. You guys agree? So this is 2 by v sine theta, and on substituting r we have mv sine theta by qb. This is on substituting r. So we have m sine theta, v sine theta common. So we have t to be 2 pi, and we have m, and we have qp. Okay, something is wrong. So that's our time period. So you guys need to conclude stuff for your conclusion. So what is the conclusion? It depends on the velocity, it depends on the charge, mass, angle, and the magnetic strength itself, similar to what we did in the last derivation. Here again, we have to conclude. So that is something that you guys should be doing. That it's not dependent on the velocity, but it depends on the mass, charge, and B, same as the last one. Agree? And finally, what do we have? Pitch. So pitch definition in regarding to in the context of helical path taken by the moving particle in a magnetic field. Pitch is defined as a distance the particle travels parallel to the magnetic field. So that's your parallel line. This is parallel to magnetic field. Okay. Where is it? Parallel to the magnetic field during one complete revolution. So if I go round once, whichever point I had considered before, if it comes back a bit above or below, that's your pitch. That length is your pitch basically. So how do you figure it out? How can I find the distance? Yes, how can I find the distance? It's a very simple, sorry, not math. It's a very simple thing. Again, your, sorry, not distance, in this case, displacement will be equal to your velocity into time. So what velocity? What is the component upwards? It's the parallel component. So parallel into your time period, right? So for this particular case, it will be parallel component in time period. So what is the parallel component? Cos theta. What is the time period? We just saw that 2 pi m qb. That's your expression. Okay, bit of rearrangement, and that's your pitch value. Okay, guys. Right? So very simple thing. All we have to keep in mind is that the parallel and the perpendicular component, they play a role over here. Parallel component it will make it go up, while the perpendicular component will make it go circular. As simple as that.